Here we are once again in Firing of Ceramics, still in unit number 2. We're at class number 14, and this is our first kill simulation exercise. We're going to use eSolutions for that exercise, the Honeywell program. So I hope you have that available for today. If you don't, you might want to pause and make sure you have it. So where we've been in unit 2 is to get the fuel to the furnace and concentrate it in burners so that we can have the heat concentrated into the furnace. And you'll recall that in the modern world, we've learned to have very high heat concentration in areas called burners. So there was a whole lot about controlling the burners, linking the gas input to the air input, so you'll be on ratio and things of that nature. And we also talked about pulse combustion or step fire. So we talked a lot about safety as well. Last time we talked about refractories and introduced furnace simulation a bit. What I said about refractories was an overview. There's a lot of technology in refractories, and your refractory supplier is going to be very pleased to educate you about the properties and use of their products, the proper use. Okay, so we've looked at heat flow as a simulation of furnace walls or other parts of furnaces. We have some environmental conditions. We select our products and we arrange the products in layers, if you will, multi-component linings, and we're able to compute the heat loss and heat storage and something about the expected temperatures at interfaces and at the outside shell of the furnace. We used eSolutions to do the same thing. I think we talked last time about expecting a little different data from both programs, but nevertheless, we're going to get started today with our first simulation, and we'll do 3 of these. The next 2 classes will be about different furnace simulations. To get started, we're going to look at some of the problems from the last time where we set up a lining design with heat flow and eSolutions. And so we're really trying to look at the heat loss and heat storage in different kill designs. I know that eSolutions gives us the whole furnace to deal with. We're going to only look at the wall orientation in either heat flow or eSolutions. So they're going to give a little different answers. Nevertheless, they have different data in their databases, whereas thermal ceramics is very specific about product names and densities. eSolutions is using generic data for that class of products. So you would expect different answers. It's not a problem if you only have eSolutions available. If you haven't been able to get heat flow, keep trying, because it's a nice utility to have. Contact the Morgan Thermal Ceramics people and they will help you. So nevertheless, let's get started. And so we set up a problem with a wall orientation with an ambient temperature of 80 degrees Fahrenheit in inch-pound units, and we're going to have a furnace interior temperature of 2,500 degrees. So that's a pretty common temperature for clay products as a temperature, maybe some refractory products at that temperature. And we're going to assume an ambient velocity of 0 feet per second, still air. So that's how you set up heat flow. We'll go through the steps for doing that with eSolutions. You're going to open the app. We're going to pick no opening because we really don't care about flue losses at this stage of our classes. We're going to choose refractory construction, refractory components as given in the problem. And we're going to read heat flux calculations through the wall. Now the heat flux, intensity of heat coming through the wall per square foot per hour is going to be the same as the heat loss that the heat flow program gives you. We'll look at the heat storage in the walls. We'll read this information and record it. You might want to note that the default design includes a steel shell in eSolutions, so you don't have to add it like you do in heat flow. The default ambient velocity is just under 2 miles per hour, or excuse me, under 2 feet per second. So here's the problem that was set up. You know, you were given an inside refractory lining that's exposed to the furnace environment, the high temperature environment. Then there's a layer number 2 of insulating material, and layer number 3 was just carbon steel, okay, as a steel shell. So if you did this product correctly, you had to add the high heat duty fire brick data to your thermal ceramics program, and I provided that data last time. So layer number 2, I said, was K23 insulating fire brick, IFB. K indicates the thermal ceramics number, K-23, 2300 degrees Fahrenheit, UD rating 4.5 inches. The reason I use 4.5 inches is a 9-inch straight refractory brick. A standard brick in the United States has dimensions 9 by 4.5 by 3. So you can see that this brick is laid flatwise on the larger area surface of the brick, and it makes the lining 4.5 inches thick. Same with K23. With eSolutions, I just had to use fire clay brick because that's their designation, and I had to use insulating fire brick. I didn't have a specific name. Now, in the program I'm using, K23 is number 116. So in using heat flow, it's really easy to add that number at the bottom, hit return, and you'll go right to K23 if that's what it is in your program. When using the program, I always kept a little list. So once you've got the data entered, you're going to set up the environment. In particular, you're going to have wall orientation, the ambient temperature, the furnace temperature, and you're going to click on slot number 1. You're going to pick high duty insulating fire brick, go down and pick it here. After you've clicked up here, double click on the product. It will show up. You put in the thickness, 4.5 inches. Then you click on slot number 2 and find K23 insulating fire brick. After you click on it, then you'll double click on K23. That enters it, get 4.5 inches. And carbon steel, you click on the cell, find carbon steel. I guess it's 0.12 inches in thickness of carbon steel. And once you've got all that data entered, you just click anywhere and it's going to do the calculation. Now, this is a little hard for me to read looking at a backlit screen. You might be looking at another device. Typically, in using those devices, I will give you a couple of different ways of looking at the information. Now with eSolutions, you set up the model, you hit calculate. We're only interested in the walls, but you might have set up the rest of the furnace as well. And you're going to get a heat flux number through the walls. That's going to be analogous to the heat loss through the walls in eSolutions, excuse me, in heat flow. And we're going to get a heat storage. Now, just to make it a little bit easier for you to see on any device, I've cut and paste these diagrams. So of course, eSolutions give you an exterior temperature for the wall. It gives you an interface between the interior layer and the outside layer. It's going to give you the inside furnace temperature. It tells you something about the thickness of the material that you've chosen, and you'll see the hearth temperature typically always higher than any of the other temperatures, and of course the crown exterior temperature. So get a lot of information here, but we're mainly interested in the sidewall, which in this case is 810 BTUs per square foot per hour. Energy transmission through the furnace, and it looks like we have a sidewall heat storage of 15,672 BTUs per square foot. So that gave us a couple of places that we could enter the data. And what we find is that when we do these, for reasons that are hard for me to explain, they get a very high number here for the interface temperature with the heat flow program. As you go out to the exterior temperature of the furnace, we get 287 degrees Fahrenheit from heat flow, 336 from E-Solutions. So they're a little bit different, but at least comparable numbers. Heat loss 575 with heat flow 810 with E-Solutions. Heat storage 35,000 BTUs per square foot or thereabouts with heat flow, and we only got about 17,000, about half with E-Solutions. So we got getting some different numbers. There are some explanations for that. We also saw that as we look back with heat flow, we got a red number up here where the furnace interfaces with the hot face, the high duty fire brick 2500. It's in red because the database shows that the maximum use temperature for a high duty fire brick is 2400. So that is one of the problems with this design right here. Probably in a real furnace, you'd use super duty refractory if you wanted to use a clay refractory brick in that situation. But that's not what we have in the database. Okay, on to problem 2. And in problem number 2, I used a dense castable. The key thing I was looking for is crete. That usually is taken out of concrete, and that's usually a dense or heavy castable. Light, Kaolite, is generally a lightweight castable. So those are the numbers that I have in my program along with the carbon steel. I use the same thicknesses here, 4.5 inches, both layers here, just to give us comparable numbers. And of course, in E-Solutions, I just picked castable insulation for the inner layer and lightweight castable for the outer layer. So then you're able to run those programs. Okay, so when I ran heat flow, you can see I got another red flag here. It said I had an interface temperature of 2188. Okay, and it said that that was too high for this material. Now, Kaolite 2200, excuse me, Kaolite 2000 is 2000 degrees duty rating. So 2188 is over the duty rating of that material, and that's why that popped up like that. A nice feature of this program. When I ran the solution in E-Solutions, you can see the double layer, the dense castable, the insulating castable here. You can see the exterior temperature of 288, interface temperature of 1272. The heat flux through the sidewall was 561. The heat storage through the sidewall was 13,068 BTUs per square foot. So you can fill in all that data, and I hope your solutions are similar to this anyway, with a heat storage of 30,000 or thereabouts, with heat flow. These people don't, these people came up with that number with their materials. With eSolutions, I came up with 13,000. So that's a fair amount of difference in heat storage. Heat loss, 442 and 561. Those are comparable numbers. Interface temperatures are at least better this time, 2188 for heat flow and 1272 for eSolutions. Now, I'm going to tell you that when I started looking at my particular heat flow data, I went in to look at the specific heat, and the program that I am using has no specific heat listed for any of the refractory materials in the database. I don't know if that's my fault or some other kind of fault, but so there is a reason why perhaps we're getting a lot different heat storage numbers between the two programs. At least I would think that would be something to be very suspicious of right away. Okay, so we've done an exercise with brick, linings, castable components in the lining. Let's do one with modules, fiber modules in the lining. So I picked Pyrostack. That's one of the thermal ceramics brands in my database, number 209 in the program I'm using. I can only pick a ceramic fiber in eSolutions. So I use 12 inches. Carbon steel shell, there's none required in eSolutions to do the program. So let's get about the business of looking. And when I did this, you can read down here, cold face temperature 197. You can look at the heat loss, about 268, heat storage, about 3,200 or thereabouts. You can look at some of the interface temperatures up here that are predicted with that lining configuration. With eSolutions, just showing you cut and paste images from the solution, I get 175 on the outside of the wall. I get a heat flux of 205 BTUs per square foot per hour. Heat storage is only 1900 or thereabouts in the wall with the fiber lining. Well, that is the advantage of fiber linings. If they're mechanically durable in your furnace environment, they save a lot of money in heat storage as well as heat loss in a furnace wall. Particularly, or you're going to notice that in a intermittent kiln because of the heat storage that occurs on each heating cycle. So here we are. You can compare these. They're comparable here in terms of cold face temperature, 175, 197. Heat loss, 269, 205. That's the best agreement we've had. And heat storage, well, once again, heat flow for some reason is giving us more information than we have in eSolutions. So that's pretty much your homework. I hope you've done this. If not, I urge you to go through this and become familiar with this simulation modeling. Okay. So we have differences in the models. And first, if we focus on heat loss, in the first point there on this slide, well, there are some differences. Probably mostly due to different thermal conductivity values in the database. Whereas eSolutions, as I mentioned, that's kind of an average for a product class. Thermal ceramics has very specific data for each one of their products. Now, I'm familiar with how thermal ceramics, Morgan Thermal Ceramics in the US does a lot of thermal conductivity testing. They have the guarded hot plate method for thermal conductivity that's specified by ASTM for refractories, and they do a lot of that testing. So I have confidence that those are good numbers. eSolutions takes kind of an average number. Now on heat storage, since my version of heat flow has no values of specific heat. I have to guess that anything that my program has predicted is way understated. This may be or may not be the case. We talked a little bit about safety considerations last time. Remember that we don't want a human being to touch the outside shell of a kill and get burned. We don't want their flesh to get scalded. So we talked about temperatures that would cause that to happen. So it's probably best in industrial practice to always be measuring those shell temperatures so that you're sure that you have protective apparatus in place if you need to keep people away from touching the side of the kill. The same is true for any possible air leaks, which I call stingers, emanating from openings in the kill. Okay, well, let's go to our first kill or furnace simulation. Now, this is going to be a pretty simple problem. This problem was one that I saw first in a training session, computer training session for the eSolution software when the company was in Hauck before Honeywell acquired them. It's a good program just to get started with, and so I'm using it here where we're heat treating 2 steel coils. So I know it's not a ceramic process, it's a heat treating process, but it's using a ceramic kiln. And one reason that we started with this one is there are no internal changes, no endothermic reactions of any note in this heat treating process. So all we have to worry about is the amount of energy required to heat up the coils in the kiln. So that's why we started in this direction. In later classes, we're going to consider situations with endothermic reactions. So here's my little drawing looking down on a shuttle kill car. So we're looking down on the car deck. This is not to scale, but the dimensions are 15 feet or about 4.5 meters. The length of the car that goes into the kill is about 30.2 feet or a little over 9 meters. So that car is a refractory deck, of course. It's going to have skid rails arranged perpendicular to the load. The load's in red. These skid rails just allow you to set the load, which is 2 coils here shown in red, right on top of them. You do that to protect the refractory and to encourage heat to transfer around the coils. So in this particular case, the skid rails or supports are made out of A309 stainless steel. Well, this furnace is heated up to 1500 degrees Fahrenheit or 915 Celsius. So it's not a particularly high temperature process. So the coils are shown here, the steel coils. The dimensions are given in inches and centimeters here. 48-inch diameter coil or 122 centimeter diameter steel coil, and that's 1020 carbon steel. Why was that picked? Well, that number is in the eSolutions database. That's why we have 1020 carbon steel that we're using in this example. The furnace height, which we don't care about for now, is 12 feet, about 3.6 meters. Ambient temperature is 60 degrees Fahrenheit. I set up this with the furnace initially at 100 degrees Fahrenheit, just to say the furnace had some residual heat in it when it was used. That's not too important to worry about. We're going to heat up to 1500 degrees C, and then we're going to turn the furnace off. We're going to shut it off. We're going to heat at 50 degrees an hour, 50 degrees Fahrenheit an hour. Typically, refractory linings are heated up at 50 to 150 degrees Fahrenheit per hour to prevent thermal spalling, particularly when dense products are used in the lining. So that's about 28 degrees C per hour. So we shut off the furnace when we get to the peak temperature. Now this is repetitive. This is some of the furnace data that I've already talked about here with dimensions and some of the other information. So I won't reread that because I've already talked about it. Ambient conditions, 60 degrees Fahrenheit, use that in the enthalpy calculation for the load, because we're going to have to heat up the steel from 60 to 1500. The steel, coils, and the skid rails are the load in the furnace. That's what we put in the furnace to be heated. We talked about the furnace schedule and we talked about shutting it down. You're going up a total span of 1440 degrees Fahrenheit and at 50 degrees Fahrenheit an hour. So it's going to take you 28.8 hours to heat up at that fairly slow heating rate. So I've already talked about the load, both the coils and about the skid rail pieces. So we can go forward. We're going to have to also set up the furnace insulation. And I've given you the crown as ceramic fiber. The sidewalls as that fire clay refractory, 9 inches this time. 9 inches is meaning that the bricks set a little different in the kiln than in previous examples. We've used the 9-inch direction as the lining thickness. And 6 inches of refractory castable backing it up, refractory concrete. The car design is 9 inches of dense fire brick, very typical to give a hard surface to a car deck, with 5 inches of refractory castable underneath. So today's job is to determine the total heat input to raise the load in the furnace to the soak temperature and include the heat losses by thermal conduction through the walls as well as thermal storage. We are not in this particular example including any flue losses. We know a real furnace has to have a flue, but we just wanted to make it as simple as possible at this point. So we're going to start with the calculations on the furnace load. So you're going to go to the properties of solid materials, and we have 2 coils and we have 6 piers. So the weight of the coils is the density of the steel times the weight of the steel. And the density of the steel is coming from physical properties of solids. So we're going to choose 1020 steel up here, and we're going to read a density. So we have a density for our calculation purposes. So 1020 steel is 488 pounds per cubic foot. Okay. If you think in metric terms, just bear with us. We're going to talk about inch-pound units in this particular problem. But nevertheless, you would probably have kilograms per cubic meter or some similar name like that. So when we do that, we can calculate the volume from the geometry of 225 cubic feet. So the weight of the steel is the volume, the density times the volume. And I said 6 coils here, and there's only 2 coils. So I believe the number would be right. I don't understand why we have a 6 here. Likewise, for the piers, I'm thinking about 6 piers. Okay, so the density of the A309 is 501 pounds per cubic foot. The volume of the piers is 37.6 cubic feet. So that allows us to calculate the weight of the piers, skid rails. Then we go over and want to determine the enthalpy. Now, in these solutions, it's really pretty easy to do that. So if we choose enthalpy calculation, and here we choose the material and go from the starting temperature 60 degrees Fahrenheit up to 1500, it will tell you how many BTUs per pound you have to add and going from 60 to 1500. So in this particular case, it's 226.2 BTUs per pound. We've got 219,698 pounds. So that's going to be 49.7 million BTUs in order to heat up those two coils. In a like manner, we can do the same thing for the piers. We calculate 112,725 pounds times 192.4 BTUs per pound to raise them up between 60 and 1500. So that's 21.7 million BTUs for those 6 piers. Of course, one thing you would want to ask yourself is, do I really need 6? I mean, that's taking a lot of energy to heat those up. So the heat required by the load is the heat required by the coils to raise them in temperature, plus the heat required by the kill internals or the piers or skid rails. So 49.7 plus 21.7, that's going to give 71.4 million BTUs as the heat required by the load. So we're getting along in this problem. Now we're going to have to compute the heat loss and heat storage in the furnace. So we're going to go into eSolutions. We're going to go into furnace heat losses. We're going to put in the dimensions of the furnace, give the furnace temperature and ambient temperature. Now here, I used an ambient temperature of 60, even though I said the furnace was a little bit warm to start with. The difference between 60 and 100 in terms of energy calculation is not going to be much. And what most people do with these calculations is try to look at a worst case scenario to figure out how much energy that we need. So given that, you set up the program with the lining design that's been given to you, and you hit calculate. And when you calculate, in this instance, we're looking at the total furnace heat storage and heat losses down here. Back when we were comparing the heat flow program to eSolutions, we were looking at fluxes through the wall and storage per square foot through the wall, but now we're operating the whole furnace. So we know that we're going to have heat transfer and storage through the crown, through the sidewalls, and through the hearth. So we've got to look at all those. And so here's the total furnace in terms of the temperatures that you expect: outside, bottom, top, inside, interface temperatures here. They're given to you in the program. So having done that, what we're really looking at is the heat losses in BTUs per hour. And it's a little over 500,000 BTUs per hour, 0.56 million BTUs per hour. Heat storage is 5.5 times 10 to the 7th. Well, I like to talk about millions, so it's 55.7 million, or about 56 million BTUs. Remember, we didn't have any openings in this furnace, so that's the reason for the 0 there. So we're going to add all these up, okay? And so when we add them up, the heat losses, worst case, is going to be 28.8 hours times 558,468 is equal to about 16 million BTUs in 28 hours. That's the time of heating of the furnace. Now that's assuming that we're at the peak temperature throughout the furnace heating schedule. This is a steady state heat transfer program. A transient heat transfer program would be much more complicated, and beyond the scope of this, you might have such a program available for your use in modeling, but we're just basically trying to use steady state conditions in order to figure a worst case scenario. And what's wrong with that? Nothing at all. We always, in furnaces, want to have plenty of firepower and plenty of heat release capability in case the mission of the furnace changes in your organization, or you need higher temperatures for product number 2 compared to product number 1. So someone's already considered that. So I wanted to look at the values we had in 26.8 hours, 71.4 million BTUs in the load. That's going to turn out to be 49.8, about 50% of the total. If we had a flue in here, it'd be a little less percentages. Heat loss from the furnace, 16 million BTUs over that 26.8 hours. Heat storage, about 55.7 million. So we've used 143.1 million BTUs or of enthalpy in this furnacing operation. So it's pretty easy for you to take this 143.1 million BTUs and divide it by the furnace time of 28.8 hours, meaning that you've got to be able to release about 5 million BTUs per hour in order to accomplish this process in that period of time. Well, we only talked about operating the furnace up to 1500 and shutting it off, which is not a very practical way to do things because it takes time for heat to soak into something that's of larger size. So once you get to the soak condition or the high temperature steady condition where you don't raise the temperature any longer, then we only have to look at the heat loss from the furnace. So if you supply about 0.56 million BTUs per hour at the highest temperature, you're going to hold or soak at 1500 degrees Fahrenheit. So you can see that we've defined in this slide a low fire minimum condition, okay, for soaking if we were going to do that. And in this condition, we defined a high fire minimum condition for heating up. So it's quite a bit difference, 5 million BTUs per hour, and here about 0.6 million BTUs per hour in this process. Well, the real fun gets to be when you've done this program and you can say, what if? So given a process, and let's face it, we're all pretty much given a process to conduct. What if I change the configuration of the lining? So case number 1 was the one we just did. Case number 2, we'll do case number 1, conditions, geometry, everything else. We'll add a flue. In case number 3, we're going to do case number 2 with the flue plus insulating fire brick in the outlet layer, outer layer of the walls. Case number 4, we're going to add a coil. I guess I figured at some point in time you could add another coil to that and try to get more productivity out of your furnace. I guess there was interior furnace space available to do a third coil. Case number 5 was the same as case number 4, but now we've used ceramic fiber in the sidewalls. Case number 6 was case number 5 and heat at a much higher rate than we were before. And case number 6 was, case number 7 was the same as case number 6, plus 1 coil plus 5 inches of the ceramic fiber in the sidewall, a little less ceramic fiber in the sidewall. So you can see that what we're doing is playing around with the refractory lining, the insulation in the furnace. There's a little key here that tells you about the dimensions of the flue. You're going to need that to do the problem. And some of the terminology that I used up in the table. And of course, the plus sign means I'm adding something new to a previous condition. So I suggest that you do this. You can pause the presentation and do a screen capture and capture this data and print this so you have this information available for you to work with. Okay, well, we used heat flow and e-solutions and compared some of the numbers in the homework problem and found out there were some differences due to the database values that were in the programs. A furnace simulation is best thought of as a prediction for heat requirements in a process. You should not use it in design of a furnace, but only a simulation or prediction. People that design furnaces have years of practice and more sophisticated tools for doing calculations like we have done. So you need to rely upon furnace designers, qualified furnace designers for exact designs. And that goes for combustion systems as well, because we've calculated the minimum heat requirements for our process, but I really respect people that supply combustion equipment like Honeywell and North American in the United States, and they are to be consulted. Safety requirements are always foremost when we begin to talk about any operation of furnaces, both with fuels and with shells and with leaks and things of this nature. So for next time, I want you to do your homework. Okay, thanks for putting up with it, but by manipulating the programs, I hope you have both. If you don't, just e-solutions, which is what you need for next time. You don't need heat flow for next time. By manipulating e-solutions, I think you'll have a little experience in practice in furnace lining design and what creates more efficient production, either by using more of the volume that you have in the furnace or by using a different insulation scheme to reduce heat storage and heat loss. Now, next time we're going to look at a kill simulation that has a major endothermic reaction on firing. You're decomposing a compound on firing a ceramic material, and we're going to do that with an intermittent kill, a batch kill, and we're going to do it with a continuous kill, a rotary kill, and we're going to do that using e-solutions. Fortunately, it has that capability. So I'll look forward to meeting with you next time. Please do your homework, and we will get together at the next class.